Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about partial derivatives, which are basically derivatives that we use to, well, for functions of several variables, right? Um, so in Calculus 1, if we were given some function, so in Calculus 1, if we were given some function y equals f of x, we take its derivative. And basically, when we take its derivative, we call this some slope, right? We call this a rate of change of a 2D plane, of a curve in a 2D plane, right? So that's in Calculus 1. But let's say, what if we were to take a derivative of a function with two variables, right? So how do we do that? Well, in general, let's say if f has two variables, and we'll just say that's x and y. Suppose we let only x vary while, okay, what is this? While keeping y fixed. We could do that. And we say b is a constant. Yeah, so if we're given two variables, then how do we do it, right? Well, okay, the buildup is very slow, but I'm just gonna go through it. Suppose x is the variable, right? And we keep y fixed. So let's do that. Suppose x is a variable and y is fixed, right? Let's say y is equal to b and b is some constant. Then we are really considering a function of a single variable x, right? So maybe then we we basically have a function, a function of single variable. So that's gonna be, I don't know, let's use g of x. Let's use g. So we say that's mainly g of x, which is f of x, comma b, right? So here the idea was b is some constant number. Here x is a variable. And let's say if g has a derivative at a, then we call it the partial derivative of f with respect to x at ab, and denote it by f of x or f sub x ab. So let's write exactly what I just said. So if we say g has derivative at a, then we have a partial derivative then we basically have a partial derivative of f with respect to x at the point a, d. So that's going to be f sub x ab, right? Yeah, initially there was an example here that focuses on limits, but it's really just going through the limit definition. So I'm not gonna dive deep into that anymore. Yeah. Okay. Um, so actually, let me do this because I'm trying to follow what the textbook is doing. Let me just do that. And here, this is basically the uh, partial derivatives of functions of two variables. Partial derivatives of functions. Okay, I can't see. Of two variables. Okay, right. So now we have that. Um, okay. So here's the proper notation for what I just said. Here we're saying that the partial derivative with respect to x is AB. It's just my derivative at point A, where my function g of x, well, is simply f of x v, right? And that makes sense. That's basically what I said in English. I just made it a math. Uh, and so, okay, here we're deriving stuff. So when we remember the limit definition of a derivative in Calculus 1, um, it's basically, okay, let me just do a brief recap. So let's say let me do a recap of Calc 1. So here the idea was, let's say we were given some function, right? And in this function, we want to find the tangent line at a point x, right? So how do we do that? Well, we actually just use a limit definition here. So we say the limit, actually let's do a graph. Okay, I'll do a quadratic graph because that one's easier to do. And let's say we want to find let's say at this point, we want to find the tangent line at that point. This is my f of x. Let's say this is x. Then this is my y, right? And I want to find, yeah, this tangent line or the slope of this tangent line. Well, then I do a limit as my h, or it's just any value, honestly, where I have my f of x plus h. So I have a value up here, maybe. This is my this is my f of x plus some h value, right? And then so that means this here is x plus h, right? And so I subtract that to my f of x over, right? Because that's how we get the slope, right? We look at my change in y, and my change in y is this one. That's my change in y. Oops, I wrote x. Over my change in x. So what's that? X plus h minus x. And so that's just the limit. Or let me. Okay, so in other words, let me do this actually. So it's the limit of my h approaching 0 of my change in f, my function, over my change in x, right? Because that's just a slope. That's what the slope is. Then we get this, and then here we can just subtract the x's. So we should get the limit as h approaches 0, f of x plus h minus f of x over h. And now why does it approach 0, my h? Because if my h is exactly 0, I get to be at this point, right? If my x plus h is equal to x plus 0, right? Well, then I just get x. And so basically, as I get closer and closer, or as my h approaches 0, either from the left or from the right-hand side, then I will get that tangent line. And this is the same as the derivative of my function at that point, right? That's a brief recap. What else? Yeah, so this is just a recap of what in the world I'm trying to say. Because I didn't do any Calc 1 videos, so I'm just explaining this part. Now, if we do partial derivatives, now if we look at our previous discussion here, and by the definition of derivative, so that's the definition of the derivative. It's the limit definition. Well, here we're seeing, oh, okay. So this, and then we just copy my limit as my h approaches 0. So I did do a little bit of limits. Pretty sure I solved one, but I know that's not enough. So I might make more videos on this. At least just to get the basics down. Here we subtract g of a. So here I'm just copying what I just did a while ago, right? So that's the definition, right? And from here, now we have another definition, which is my f sub x. This is equal to, well, that limit definition. But here, we use f instead of g. And so we say f of a plus h, comma b, right? And then we subtract that to my original function. Then we divide it by h, right? Let me just... So now we are considering a function of several variables here. So what we did before, and then what we just added, we added this b. That's all we added. But otherwise, the notation is pretty much the same. And we could also do it for y, right? Similarly, if I do the partial derivative so here I'm writing it in English, of f with respect to y, let's say at this particular point at db. And so this is just, well, f of f sub y db. So here we keep x fixed. So this is now the time where we keep x fixed, and we find the ordinary derivative at b, right? So here we, so from the previous one, we keep y fixed, But here we keep x fixed. Did I say that? Oh crap, I didn't say that. Oh no, here yeah, I said it. Y is fixed. Here we keep x fixed. And so we say x equals a is a constant, right? So let's say a function of y is just f of a y, where y is the one that varies, a is the one that's fixed. And so from there we have another definition, a limit definition again. F sub y is a comma b. And here we have the limit definition as h approaches 0. And now here a is fixed, right? And then we subtract all over h, right? Okay. With this notation, for partial derivatives, okay, it goes through the particular example from before. I'm not going to go through it. Now here's the fun part. What if we let both points vary? So if we let this point vary, so meaning both of them are variables now, instead of one of them being fixed. Now f sub x and f sub y become functions of two variables. Now they are two variables. So what does that mean? Now we have two limits. So we're saying f sub x and f sub y. Now here we go back to a previous concept from the last video. Now they become functions of two variables, right? So how would that be? Well, okay, let's go again. So my number 4, here we're going to unlock a definition. So this is going to be, well, if we have some f, and let's say it is a function of two variables. Now we have partial derivatives. Its partial derivatives are defined by these two. So we have f of x, x comma y. Here we assume that we have two things. So we have f of x plus h comma y minus f of xy all over h. That's the first thing. The other thing is f of y, xy. And here's its limit definition. Subtract. There we go. So that's another important definition that we have to cover. And there are many alternative notations for partial derivatives. Yeah, I mean, there are alternative notations. Instead of writing f sub x, we could write f sub 1, right? We could do that. Or we could even do d sub 1 f. Just to indicate differentiation with respect to the first variable. Or we could write it like this weird looking f. But they can be interpreted as a ratio of differentials. So that's the only caveat there. We cannot interpret this as a ratio, like what we did previously before with functions of a single variable, where we take its derivative like this. Here we could interpret this as a ratio. So that was convenient, but here we don't. But I mean, you can't really tell. So yeah, let's just write down the notations for each. So notation. And this is specifically for partial derivatives. Okay, let me just write them down. Here we do a statement. If z is the output of a function of two variables x, y, then we basically have these. So we can either write them as f sub x. So that's the notation we know. We could write it as f sub x without the xy. We could write it as this cursive d. I'll call it a cursive d, unless there's a name for it. Actually, let me write that a bit nicer. There we go. Not too bad. We could write it like this. So this one is the other notation that we previously used in Calculus 1. Another way is the derivative of z. That's another way. And this is in terms of x. Another way is f sub 1. Another way is d1 or d sub 1f. Another way is d sub x f. So again, it really depends on what we're trying to go for here. Then here's just everything in terms of y. Right? So now that's everything in terms of y. Now that's a lot of notations. How do I know which one to use? I'll use what my professor uses. Yeah, when I'm doing homework, I'm just gonna use that. And here we have partial derivative of z with respect to y. And here it's actually simple because we're still taking the derivative, but we're doing it for both variables. I think that's how we do it. Oh, this is also 2 instead of 1 to indicate that it's the second variable that we're looking for. So those are the notations of partial derivatives. And to compute these, well, all we have to do is remember from equation 1 that the partial derivative with respect to x is just the ordinary derivative function. That we'll call it g of a single variable. So the idea is that, okay, let me write the rule. So the rule for finding partial derivatives is that, well, we want to, okay, let me write the complete thing. The rule is that, okay, number 1, we find f sub x. So we focus on that first variable. And here we say y is a constant. And then we differentiate our function f with respect to y. So we take the derivative of our two variable function with respect to y. We're going to see some examples of how exactly this works, right? And next, to find f sub y, now we make x a constant. And we again differentiate my two-variable function, but this time with respect to x. So what do I mean by that? Well, let's look at an example to see what I mean. Okay. Example. Let's say if f of xy is equal to this function, x cubed plus x squared, y squared minus 2y squared. Now we want to find f sub x do 1 and f sub y do 1. So let's see. So the first thing we want to do is differentiate with respect to x. Why do we do that? Well, we're trying to find, and if I did it. Oh, so we're making x the input. So if we say we differentiate with respect to x, we're making y. Am I right? Wait a minute. We make y constant and we differentiate with respect to x. Oh yeah, so we make what? Respect to this one's okay, that one's wrong. I wrote it wrong. Respect to what? Y a constant differentiate with respect to x. So if we're finding this, we make y a constant and we differentiate. Why is it y? Oh, so I have it in reverse. My bad. I was just so confused. And then this one's y. Okay. So to do that, well, let's do it, right? So first I need to take the derivative with respect to x of this function here. So x cubed, what is that going to be? That's 3x squared. Plus x squared y cubed, what is that going to be? Well, if we take the derivative of that, that's a product rule. X squared y cubed. Here we do a product rule. So we're saying x squared derivative times y cubed plus x squared and the derivative of y cubed. So what do we notice? Well, this is just 2x. No chain rule, no. This is the same. This is still a y cubed. This one's still the same. This one is 1, right? Because if we treat this as a constant, I don't know, 8. Let's say y is 2, I don't know. We get 1. And so we have 2x y cubed plus x squared. And I hope I got that one right. Let me double check. Okay, apparently it didn't, so that's funny. Or I'm just okay, because okay, let me see. So 2x y cubed plus x squared. Let's see if we got that. Now I have to differentiate that last term, which was minus 2y squared. So let's quickly do that. Well, here it is just a number. So it's just 1. We do plus 1. And this might be it. X squared y cube. Oh no, did I mess something up? Oh, because I treat this as a constant. Oh my goodness. So basically, I treat it like a number. So I imagine this is some number. I imagine this is some number. I just put it at the front like I don't care, and I do 2x. So I get 2xy cubed. And then this one is just some number. So that's going to be 0. So it should be this. Okay, never mind. There we go. And then from there, let's plug in. So we're being asked to find this value here. Well, now we just plug in here. Plug in the 2, plug in the 1. Then we get some number. We get 4, 3, 12 plus, let me just do this, 12, 4, 16. And I think that's it. Okay, cool. Nice. Okay. Uh, Now what do we do next? Now we differentiate with respect to y. So that I can find my y values here, right? So let's quickly do that. F sub y. Yeah, I'm not gonna do it in limits anymore. Why in the world would I do that when I have these? Um, so again, let's look at my function. X cube is a number. So that's gonna be a 0. Right? This is gonna be a 0. This one, this is a number again, x squared. Y, let me just do this. This one has 3y squared. And this one again, I don't know what this is. Negative 4y. So here we actually have x squared, 3y squared, minus 4y. There we go. Maybe just to make it cleaner, I'll put the number up front. So I get 3x squared y squared, because that looks cleaner, minus 4y. And now we plug in my 2 and my 1, and I evaluate. There we go. What's this? 4, 12, minus 4, 8. Done. That easy. And then 16. Okay, while I'm at it, I might as well do some exercises in my homework. I'm trying to attack these problems. Like really, really, really hard. Let's do it. So let me just attack some of the problems I have here in my homework. Can I do that? I don't know. Make a new page. Oh yeah. Yeah, we have like 16 stuff here. Determining signs. Not really gonna go through that anymore. Oh, there we go. Okay, let me do some of these. Okay, one of the items here we're being asked okay, goes to number 4. I don't really mind. Here we're being asked to find the first partial derivatives of the function, of a particular function. I'm gonna assume it's f. We'll call it f. X, y. So it's a function of 2 variables in this case. This is equal to x6, x to the power 6 plus 6xy to the 9. Okay, so here we want to find f sub x. So let's do that. So here we treat y as a constant, because that's what we did here. If we're trying to find something with respect to x, we treat y as a constant, and conversely, if we were to treat if we were to differentiate with respect to y, then we treat x as a constant. So let's quickly do that. Here we're treating y as a constant. So let me just take its derivative. So y is a constant. This one is not. X to the 6 is just 6x to the 5. 6 stays the same. X becomes 1, right? Actually, there's an easier way to do this. Let me take out my 6 and y to the 9th are constants. So this could be a number on its own. I could say like 6y to the 9th x. Then I treat these as a number. Like, I don't know, 5. I don't even care. I can treat it like a number. So if I treat it like a number, and then I have my x here, I take the derivative of this x, well, I get 1. So I just get 6y to the 9th. Done. Let me just double check if I got that. 6x to the 5th. I added the 6y to the 9th. I should get the number I'm looking for. Not the number, I should get the answer. Got it. Okay, now we do f sub y. And here we, again, take the derivative, but here we treat x as a constant. So if you want to treat x as a constant, well, now this becomes 0. X to the 6 becomes 0. Now we look at 6xy 9. What is that? 6 is a constant. X is a constant. So we treat it like this. 6x, y to the 9th. Here, this is just 6x. We leave it as is. Here we treat this. We take the derivative of this. So we get 6x 9 y to the 8th. And we can just multiply, so we get 54x y to the 8th. Right? So that's how we take that derivative. Great. Let me just type that in really fast. Oh, 54xy to the 8th. Nice. Okay. Let's do one more. Number 5. Yeah, I skipped like 3 numbers here. I might do them later though. So here I'm gonna copy paste because we're being asked to do the same thing. So again, we want to find, oh, why did I take a screenshot? Here we're trying to find the first partial derivatives of a certain function. So again, we're just gonna do the same thing. So here it's really just getting used to this idea of partial derivatives. No, I can't. Great. No, I can't. Okay, this is very convenient. Now I cannot go to my pen. Let me exit. Okay. The technical difficulties are emerging. Now we share. Okay. So I always shut down my OneNote if my pen's not working. So the function was, now this is f of x t, right? So it's just a different variable. Like it doesn't matter. Here we have t to the eighth, e to the negative x. So here we have an exponential. Okay. Let's see. So first we find f of x. So let's quickly do that. X comma t. And then we take the derivative here. So here we treat t as a constant. So we say, okay, I'm going to completely ignore this. Now I look at the derivative of this thing. E to the negative x. Well, that's just a negative, if I were to copy, negative e to the negative x. Right? Because I bring, well, I take the derivative of my outer function, I get e to the negative x, and then I do chain rule, I take the derivative of my inner function, which is negative x. That's just -1. So -1 times e to the negative x, I got negative e to the negative x. And then here I can just say negative t to the 8 e to the negative x. And that's it. There we go. Okay. Let me do f of y. No, I'm kidding, not f of y. F of t, rather. So now I find f of t. So here now I treat x as a constant, right? So here I do f of t, x comma t. Here I treat my x as a constant. So let's say I bring this up front. I leave that be. That's that. Now my t to the 8th is what needs to be derived. So what is this? Well, this is, I bring down my 8. So I get 8 t to the 7th. And I'm done. I could just say 8 e to the negative x t to the 7th. Or in any form. I don't care. But I should get the same answer. Let me put my t first, actually. I don't know. I'm biased. It looks nicer that way. Yeah, that's it. I'm done. Negative t to the 8 e to the negative x. So here I'm just plugging in what I answered. Okay, now we have 8 e to the 7th. And I go down. I get e to the negative 8. I get e to the negative x. My bad. And that should be it. Let's see. Nice, got it. Okay, and okay, we have a couple more of these. We have a lot, actually. Oh my goodness, we have a lot of these. Okay, we have implicit differentiation, second partial derivatives, so that's another thing. Temperatures, another thing, total resistance, and that's it. So it's mostly just about getting derivatives and treating one of the variables as constants. Okay. Let's do it. How many more do we have? Okay, there's a different notation here, but we shouldn't mind it. I'm gonna do 2 more. Let's do 3 more. I'm gonna do 3 more, and I'm gonna stop this video because it might be too long. But it's really just getting a sense of, or getting an idea of what or how to do partial derivatives. So I said I was gonna do partial derivatives in one of my previous scientific computing course videos. Now I have a function of 3 variables here. 1, 2, 3. Yeah, I'm going to do 3 more because these are functions of 2 variables. And then I move on to 3. Okay, let me quickly do some. Number 6. So here again, we're being asked to, well, do the same thing. Oh my goodness, what happened there? Okay, I think it made a screenshot out of it. Anyways, okay. So here I'm given this function, f of x, y is equal to ax plus by over cx plus dy. How do I do that? Well, okay, this is something of a quotient rule. I'm gonna say a, b, c, d are constants, right? They're numbers. Yeah, that's what being delusional is. You think of letters as numbers when you're in math. Okay, so let's find f sub x. Let's do that. So here I treat y as a constant, right? Okay. So what is this? If we were to take the derivative of this thing, well, we would do. Okay, let's do a quotient rule. Why not? So let me just introduce what quotient rule is before I move on to doing this. It's a calculus 1 topic. So I'm just going to do a brief recap. So recap, calc 1. And I'm going to say here, one of the techniques of taking a derivative given a fraction is using quotient rule. Okay, let me just, I'm going to do it for a single variable. So here we're going to say quotient rule, which is one of those techniques. And there's actually a nice mnemonic here, which I'm going to explain in a bit. This is something I used to remember quotient rule specifically. So the idea is if we're given two functions, we're given two functions. So we say if we're given some f function and some g function, and if we take the derivative of this, we're going to get the derivative of g, f times f, minus, oh no, my bad. So we do, my bad. So we do this first, and then we take the derivative of my upper, my numerator. Then we do my upper times the derivative of my lower, and then I square my lower. So what's the mnemonic, the famous mnemonic? Well, let me just write it out. That's a very catchy mnemonic. It's we say this is high, this is low. That makes sense, right? And what we do here is low times d high, which means derivative of high, minus high times d low over low squared. Low d high minus high d low over low squared. It's that, yeah, it's that mnemonic. That one's really fun though. So that's how I was able to do it. So low g of x d high derivative of f minus high f d low derivative of g over low squared. So the g of x squared. So that's the mnemonic, and that will give us the derivative of this whole thing. Okay, let's do it for in this case. All right, so we have this thing, but now we have it in two variables. Okay, so, right. We're taking the derivative of this thing, cx dy. And so we do my low first, right? So low derivative of my high. Here I like to take it step by step. I put that, what do you call that? An apostrophe to indicate I'm taking the derivative of that. Okay, I can't. This is too long. Let me put it down here. Yeah, I'll put it here. Minus high, so my numerator. D low, so the derivative of this, over low squared. And I continue. So what is this? Well, I keep this the same. And now I take the derivative of ax plus by. Now, what did I say? I said ax plus by. I said my y is a constant here. So what does that mean? If my y is a constant, b is a constant, well, this is just 0. And now I get ax. And if I take the derivative of ax, I just get a, right? So I basically get a, done. Then I copy. And now I take the derivative of cx plus dy. Again, this is 0. D is a constant, y is a constant. Now this is c, right? Over this thing. And I'm done, right? I could simplify, but I don't need to. But I could simplify. Um, yeah, I would honestly just leave it like this. But I know some things can be simplified. Like we could say, oh, if we multiply this and this, we multiply this and this, that would be 0, right? We could see those stuff. And then if we multiply this and this and this, so we basically get ADY minus CBY, and then we could factor out the y and stuff like that. Like we could play around with those values. We could even expand CX plus DY. It's another thing we could do. But I'm gonna leave it this way. Why? Because I'm not plugging in any values. So I'm leaving it that way. Okay, so let me quickly type that in. CX plus DY. Then I have my A minus my, I have it in capital. AX plus BY, C. And I do over CX plus BY. And I square that. And I'm done. Now, let me see if I got that. Because I might have messed up something. Okay, let me submit, see what happens. But yeah, that's quotient rule. Oh god, nice. So I got that one. And we do the same thing for the other one. So here we do f sub y. So first thing I would do is copy. Do a derivative sign. Now I do my low d high technique. So I'm gonna say this is low derivative of high. I could have just copied the previous one. Minus high, d low. Okay, I can't see. Over low squared. Great. Now what's this gonna be? Well, I copy cx plus dy. Now I do the derivative of this, but here I make x a number. So ax is going to be 0. By is going to be b. So I get b. Subtract ax plus by. Here, cx is going to be a number, so that becomes 0. Taking the derivative of dy, I get d, because d is a number, over this one squared. Done. As simple as that. Right? I'm actually gonna go ahead and copy paste because I have most of the answers already. In this first one. I'm just gonna change AC to BD, and then that's it. So B, if I don't mess up the letters, and D. Yeah, I should get the same answer though. It's pretty similar. And nice, we got it. Okay, number 7. So here again, same idea. Oh, I copy pasted my answer from the homework. That's funny. Let me go on. Oh, yeah, it is a screenshot. That's funny. Let me just do this instead. Copy and paste. There we go. Go down. Go down. Can I just go like there? Oh, I can do that. That's pretty slow though. I'm dragging this thing. Okay, there we go. Nice and easy. Okay, now here we're given W is equal to e to the v over u plus v to the 4. So here, if you notice, this is a function. So I'm going to write this. This is a function of u and v. Or I could write it the other way around. It doesn't matter. But yeah, that's actually the function of that. Right? So this is just to help me determine what this is. Okay, now the first thing it's asking was a derivative of w with respect to u. And so here I'm just doing f sub u of this thing. I'm just translating the problem. So here I make v a number, right? So again, honestly, I could either do a quotient rule or I could just turn it easily into a product rule, which I think would be easier. Let me do that actually. Turning it into that would be easier. I'm gonna turn this thing into a product rule. So I'm gonna say I take the derivative of 1 over u plus v to the 4th, e to the v. That way I have two products here. I could do that. And so let me just say a few things. U plus v to the 4th, I multiply it to e to the v. That's not dot product. I meant for that to be okay, because that notation's stolen. I'm gonna use that notation. So here I'm doing a dot product. So if I do a dot product again, well, I just take the derivative of the first one times the second function plus the derivative of my second function times the first function. Right? So let me just do that. We take the derivative of this, because we can. Then we do this. Plus, we take the derivative of this thing. And so what's this going to be? Well, e to the v is a number, right? So if that's a number, well, I would get what? 0. And if I multiply this, I get nothing, basically. So I'm left with this. I'm left with this. So what's that going to be? I get e to the v, so copy. Here I take the derivative of this. So what is this? Well, actually, now that I think about it, I think it would have been easier to just do a quotient rule. Because I'm either way I'm gonna do a chain rule. Either way I'm gonna do a quotient rule. So that was an extra step for me. My bad. I didn't know. So at the end of the day, I'm just gonna do a quotient rule. Okay, let me quickly do it. So again, quotient rule is low di minus high below over low squared. So what is this gonna be? Well, first I copy this thing. What is this? The derivative of e to the v is 0. So I actually just delete this whole thing because that one's a 0. Let me do this. That one's a 0. The derivative of this, so this one's a 0, right? This one's a 1. So I actually just get negative e to the v all over this thing squared. So it was actually easier to do a quotient rule instead. And that would have given me some output w. Okay, so my bad then. U plus v, right? V to the fourth. And then I square that whole expression down there. And here I get e to the power of v. And that should be it. I hope I get it. Got it. Okay. And then lastly, we do. So we're still taking derivative. Now we do it with respect to v. And so this is saying a function with respect to v. So what's that going to be? Well, now we treat u as a constant. So again, let's, I'm not even gonna, I'm gonna copy paste this thing. I know I'm gonna have the same format. I'm gonna copy paste that. Now I take derivatives. So here, oh, that's funny. Can't move. Oh, that's nice. Now I can, that's not fun. Okay, how do I do this? Is there a way I could just like go back to my pen? Because I can't, that sucks. What if I just do this? Maybe this. Oh, can't go back to my pen. Okay. X again. And then we open up my OneNote again. And then we share it again. Okay. And now I should be able to draw stuff again. Okay. So here we take the derivative of e to the v. Here we treat v as a variable, right? So e to the v is just e to the v. That's it. This one, however, u is a constant. So this is 0 plus, what's this? V to the fourth. Well, this is 4v cubed. And that's my answer. So I have u plus v to the fourth multiplied to e to the v minus e to the v. And I multiply that to 4v cubed. And I put that all over my denominator. And I'm done. Do I need to simplify? I don't need to. Is it better to simplify for future problems? Yes, when we're plugging in values, because it's way easier. But in this case, I'm not going to do it. Okay, that's it. And you can see that it's really different from It's different from our previous ones. Okay, so we have u plus v to the fourth, e to the v. The derivative of e to the v is the same, assuming that v is a variable and not a constant. You're just copying everything that I just wrote. I'm just plugging it in. V plus v to the fourth to the power of 2. Let me hit submit, see what happens. Then we're going to proceed to our last item after. Nice, got it. Okay. Now for the last item here, for now, because now I'm going to go through some other stuff. Again, we're doing the same thing. Oh, no, that's nice. I meant to do this. Okay. Maybe just go here. Oh, there we go. That was an easier way to do that. Don't know why I had to scroll it down. Okay, so we have f of x, y, and this is equal to x to the power 6y. And here we find f sub x. So we take the derivative, we make y constant. Right? So what happens if we make y a constant number? I bring this down, so I get 6y minus x to the power of 6y minus 1. Okay, why did I do a minus there? There, that's my answer. Because here we treat it like a number. Then I subtract that whole expression, 6y by 1. So 6yx to the power of 6x minus 1. Right, so I treat my y as a constant number here. Let me submit, see what happens. Oh shoot, I wrote x. Oh my goodness. Instead of y, I wrote x. That's funny. I just realized. Yeah, I accidentally wrote for my exponent. I wrote an x. I typed x. Okay, that was a mistype. Okay, got it. And then for my f sub y, see, it's one of these things that's gonna make me suffer. Well, now here I treat my x as a number. And so what happens if x is a number and my y is a variable? What's that gonna be actually? I'm curious as well. Wait, how do we take the derivative of that? Let's say x is 1. I'm gonna say x is, or no, x is 2. How do I take the derivative of this? Oh crap. That's something I haven't done in a while. Oh crap, that is something I haven't done in a while. Let me just double check some differentiation techniques. Maybe, let's say even something basic like 2 to the y. Oh, so there is a formula for that. Okay. So let's say, okay, this is just a brief review. Okay, review. Let's say we have 2 to the y. We take that by getting the natural log of 2, and we multiply that to 2 to the y, right? And then we do a chain rule of whatever's inside here. And so here in this case, if we have x to the 6y, well, I should have done it in the next page. If we have x to the 6y, I would get ln of x to signify that's a number. And then I would get x to the 6y. And then I would take the chain rule of my 6y. So I take the derivative of that, I get 6. So then I would get, I'm just completing my solution here. I would get 6 ln x, x, 6y. Done. I hope that got it. Yeah. Let me see. Yeah, that's just a differentiation technique that I totally forgot on how to do. Let me hit submit, see what happens. And yeah, got it. Yeah, so the next parts are gonna be like uh variables of 3. Oh yeah, functions of 3 variables. I'm gonna go through those in the next video. I hope you guys enjoyed, and I'll see you all in the next one.